Hi folks, so here we are, nuclear next chunk. We're here to talk about Decay Series and also the parts of a nuclear power plant. So nuclear power plant will only be for the honors, and so not in the regents. Decay Series. So remember once again what it means to decay. Decay means to break down, to become more stable than you were by giving off energy and particles. Last time we talked about the types of decay like alpha, beta, or positron. If you don't remember what those are, please go to table O on page 7 or watch the video from last time. So remember, decaying means to go from something unstable to something more stable, but that doesn't mean it is done. It's not just necessarily one transmutation, which, by the way, transmutation means changing from one element to another. So it's not always going to be just one change and you're done. It could be a series of many, many transmutations. Remember, all the way up to element 83, those are, hold on a second. Those are the ones that are radioactive. Yeah, 83 is the last stable one. So if you decay and you're still not an atomic number 83 or lower, you're going to have to continue. So here's an example of a decay series. This is just a graph. Don't worry about it. Take a look at the x-axis. We have atomic numbers, so they go up by 2s. So, for example, atomic number 80, who are you? You are mercury. And then 82, we have lead, and 84, we have polonium, etc. So do you see how at 82 we have lead? Good. But what is the mass of lead? Oh, this lead is 206. This lead is 210. Wait a second, how can lead have two different masses? Oh yeah, they can be isotopes. So different numbers of neutrons. So anyways, look at where the graph starts. It starts here. That is uranium. How do I know it's uranium? Besides the fact that it says U, it's at number 92. What is the mass of uranium? 238. Now, uranium-238 is an unstable radioisotope. It's going to decay. How is it going to decay? Well, if you look, it's going to be a series of many different ones. So, again, to define, it's a chain of transmutation in which a radioactive element decays until it reaches something that is stable and non-radioactive. So let's take a look at this graph. Every time you see an arrow that goes to the lower left, that means we're going down. Look, the mass is going down by 4. And as you see, we're moving to the left this way. That means we're moving, losing 2 protons. So every time you see an arrow that goes like that, we go from uranium-238 to thorium-234. That means this is an alpha decay. So every time you see that, this is an alpha decay. 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 Alpha decay. These little ones are not. This one is. And this one is. Hard to draw alphas. Anytime you see another kind of arrow, but this time you notice that the height here, the y-axis, stays the same, but we're moving over an atomic number. That means we are going through beta decay. So remember, with a beta decay, your mass doesn't change, but we are going to change our protons, of course. So this is beta decay. This is beta decay. Beta decay here, 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 and here. So how do you read this graph? This says uranium-238 is very unstable. It's going to go through a series of decays. So it'll go alpha decay to become thorium-234. Is thorium-234, and let me erase that for a second, because you can barely see it. Is thorium-234 stable and thus won't react again? No, it's not. So it will continue to decay. How does thorium-234 decay? Looks like it gives off a beta. What does it become? Pa. Is that protactinium? I want to say it is. Help me. Oh, elements 90 and above have been omitted. I'm going to go with protactinium. Don't quote me. Don't hate me if I'm wrong. So that is still not stable. So then it undergoes another beta decay to become uranium-234. Uranium, it's still not stable. Uranium-234. So we undergo this, become this, become this, become this. All of these decays until finally we become lead-206. Lead is at an atomic number that is stable. So it's not going to go any further. This is the end. So because you weren't stable, you had to undergo all these changes. Now, why do some undergo alpha and some undergo beta? I don't know. Everybody's different, I guess. So this is just how it goes. Just wanted to show you that it's not necessarily going to be one and done. Notice it's a series of changes. And if you can read the graph, which, by the way, there's a worksheet that you're going to have to do that involves reading the graph, you can tell what kind of decay and who it changes into. We also need to talk about other kinds of changes. So we talked about artificial transmutation and natural. Natural is when one item is going to break down all by itself and give off particles and energy to become something new. And then there's artificial transmutation is when something needs a push, it needs a boost. So that's when you have like a little neutron or something breaking it down. Then we have fission and fusion. Fission is big. Splitting a big nucleus. What do I mean by large nucleus? I mean large mass. Massive. Into smaller fragments. Well, how do we do that? Well, you need a little push also. You're going to radioactively, you're going to bombard them with small neutrons. So this gives off a ton of energy. And so it sparks what we call a chain reaction, which most people are probably very familiar with. So here we have an unstable nucleus. Blue are protons, gray are neutrons, as you can see. The neutron hits this one, splits. And so as it splits, it also gives off neutrons. Well, what do these neutrons do? They go and further split off another nucleus going on. And this will continue. And so that's fission. This is a large nucleus being split. It gives off tons of energy. So there are two kinds of chain reactions in which we undergo fission. There are ones that we control, and there are ones that we don't. And there are pros and cons to both. In a controlled chain reaction, we can get all that energy, but we can kind of control how fast it goes and get it to work for us. So controlled chain reactions are found in nuclear power plants or reactors. So we use fissionable fuel and we bombard it with neutrons, and all of that is kept in check by moderators and other control rods, which if you're going to continue looking about nuclear power plant, we'll talk about. So we are able to harness that energy from the chain reaction of splitting in a controlled way. But there are times we don't want to control it. We want it to just go. And why would you ever want an uncontrolled chain reaction? Well, we want destruction. So, sorry you can't read all that. It says a chain reaction in which energy is released extremely quickly, like in the fraction of a second. Why would you want that? You want destruction. So in the example of atomic bombs, we would take that fissionable fuel and we would just let it go. There would be no kind of controls or checks to make sure that energy and that chain reaction is monitored. We just want it to just go. And so that is an uncontrolled fission chain reaction. I'm going to skip this for now. I want to talk about fusion. And if you are in the Regents class, we're going to be done. If you're in the honors class, we're going to continue. So this is for everybody, but I'm going to go here just for my college prep chem friends. So if we talked about how fission was splitting, fusion is bringing together. We split something big. We fuse things that are small. And if you think about it, if you are splitting something, you'll get a lot of energy. But if you combine it, it's much, much more. This is only going to happen at very, very high temperatures. We can achieve it on Earth, but it happens very readily on the surface of the sun. Let's talk about this diagram for a second. We have deuterium and tritium. What does that mean? Well, looks like we've got a neutron and a proton. So 1 and 1, mass of 2, 1 proton. Okay, so if I've got 1 proton, it's hydrogen. This is a hydrogen isotope. Okay, it's called deuterium. We have tritium. So 1, 2, 3, we have a mass of 3. Still, we only have 1 proton. So hey, this is another hydrogen isotope. They come together. Notice this wobbly uncertainty. So you can barely see it, but this is a neutron given off, and it forms helium. How do I know it's helium? We've got 2 protons. What's my mass? 1, 2, 3, 4. So we're fusing these two together to form this, and lots of energy is being given off. So we can achieve this on Earth, but you got to have tons and tons of energy. It's going to be at very high temperatures. This happens naturally on the surface of the sun. If you are in the Regents class, this is where we're done. If you are in the honors class, we are going to continue. So let's go back to nuclear power plants. Nuclear reactors, not on the Regents, but definitely still important to know. I have attached a video for nuclear reactors. It's a little boring, gotta be honest, but it does give a nice overview. So nuclear reactors, we are using a fission reaction. So again, splitting of nuclei, large ones, but it's controlled. So we have things in place to help slow it down. This is 9 Mile Point, Scriba, Oswego, New York. It's a functioning nuclear power plant. We have many in the country. This might be one you're familiar with. You might be also familiar with nuclear reactors in Fukushima, Japan, which was the site of a nuclear disaster, I believe 2011. And then there was also the nuclear power plant in Chernobyl, Ukraine, former Soviet Union. That was in 1986, I believe. And we'll talk more about that. By the way, here's a plug. If you've got time and you have HBO, I highly recommend Chernobyl, the miniseries. It's a little dark, it's a little creepy, but man, is it good. Plug for HBO if you've got it. Okay, let's talk about parts of a nuclear power plant. I think most people are familiar with this. Cooling tower. This is not smoke. This is steam. We'll get to it. All right, so the first thing, obviously, you need at a power plant is the fuel. We need it to be fissionable. We need it to be able to be split. Usually in a nuclear power plant, we used uranium-235. It's enriched, which means it's removed some of the other junk, so to speak, to make it as pure as you can. So this is purified. So we use enriched uranium-235 in the form of cylindrical rods. So these cylinder rods, those have uranium-235 inside. Moderator, use your context clues. If you are a moderator, you help kind of keep things moving smoothly, kind of slow it down. These are particles that will collide with your neutrons. Because remember, in fission, you're splitting and neutrons are just blasting around like crazy. So these moderators are slowing down the flow of neutrons and helping them be more efficiently absorbed by the uranium. We have heavy water and graphite. Now, heavy water, what does that mean? Okay, thanks for this right in the way. Heavy water is H2O, but instead of using regular old hydrogen, we're using that deuterium isotope, which means it has a mass of 2. So we put a superscript up here, meaning mass of hydrogen is 2, so it's a little bit more massive. Now, people are always like, can you drink heavy water? Is it really that much heavier? Well, think about it. It's got 1 extra neutron. How much heavier could it be? Could you drink it? I'm going to let you look that up if you're so concerned. Control rods, as their name describes, they're going to help control the reaction. Again, they are also going to absorb neutrons. They might slow down the reaction or stop it altogether. So some common control rods are boron, it's elemental boron, or cadmium. Obviously, a lot of energy is being given off, so we need to try to moderate that by using coolants. Coolants maintain the temperature. They help transfer the heat so it can be used to produce the steam for those turbines. So remember that cooling tower had steam coming off. We need to keep all that heat and transfer it to steam. We use air, water, or liquid sodium metal as coolants. Those help absorb the heat and help transfer it. Shielding. Gee, there's a lot of energy and particles going on. We should probably protect our workers, and we should also protect the actual reactor. So the personnel, these are people, but also the reaction themselves, the shielding. So here we have our shielding within the containment building. If you'd like to go ahead and just study this whole diagram, that's great. Will I test you? Will I say, what is this? No, I won't. I just want you to get a general idea of the parts of the nuclear power plant. And that's where we are. So feel free to watch that video on parts of a nuclear power plant if you'd like. And again, any questions, please let me know. Thanks. Bye-bye.